distributed key-value stores. This paper proposes NetMC, a novel multi-get coordination architecture that leverages programmable switches. Okay. Modern online services need to handle a large number of concurrent requests while meeting strict service level objectives. For example, to render a single web page, a client may need to fetch many data objects from a key-value store. Key-value stores like DynamoDB, Memcached, Redis, and Cassandra are essential building blocks of these systems because they provide fast access to key-value pairs. To provide faster access to multiple keys, these systems support a multi-get operation. Multi-get allows clients to fetch the values of multiple keys with a single request. For example, if a client wants the values for keys A, B, and C, using basic get operations would require 3 separate requests and 3 responses. But with Multiget, it can be done with just 1 request and 1 response. So this significantly reduces the number of round trips, saving both bandwidth and latency. In fact, Meta has opted Multiget in Facebook's Memcached clusters to improve performance. However, today's services don't store all keys on a single server. Instead, the keys are distributed across multiple storage servers. This makes multi-get coordination more challenging because it requires extra coordination. Specifically, there are 2 main steps. First, request splitting, where a single multi-get request is divided into multiple sub-requests, each targeting a different server. Second, reply aggregation, where sub-replies from different servers are merged into a single reply, like this. So, existing systems generally follow one of 2 approaches for handling multi-get coordination. The first is the client-based architecture, where the client handles both request splitting, like this, and reply aggregation. This can achieve high throughput since the client takes full control of coordination. However, due to high overhead on the client side, it cannot provide low latency. The second is the coordinator-based architecture, where a dedicated CPU-based coordinator server acts as a middleman, like this. This reduces load on the client, but the coordinator can easily become a bottleneck. So as a result, the coordinator-based architecture is not scalable and cannot achieve high throughput. So, client-based architecture, the coordinator-based architecture, neither of the existing architectures can achieve high throughput, low latency, and scalability at the same time. This leads to the core research question. How can you coordinate the multi-get operation to achieve high throughput, low latency, and scalability simultaneously? To address this, we propose network-accelerated multi-get coordination like this picture. NetMC takes a new approach. NetMC splits the coordination work between the network switch and the client. Specifically, we offload request splitting to the programmer switch and leave reply aggregation on the client. This allows each function to be handled at the place where it's most efficient. Let's first look at request splitting. This is implemented at the programmer switch. Request splitting is stateless and idempotensive, since it just divides a request into multiple sub-requests. And then programmer switches are well suited for this kind of work because they can handle billions of packets per second at terabits. Also, switches can customize the packet processing logic in the data plane using a programming language P4. So, by offloading request splitting to the switch, we can reduce both client overhead and latency. On the other hand, reply aggregation is handled by the client. It requires stateful processing and logic for variable length data, which is hard to implement inside the switch. So it's better to handle reply aggregation at the client. However, implementing request splitting on the switch is non-trivial. Programmable switches have limited memory access because they are originally designed as switches, not CPU-based servers for complex operations. They also have limited computational capabilities. For example, they do not support loops like for, while, or even operations like modulo. To overcome these technical challenges, we simplify the switch logic as much as possible and let the client assist the switch by embedding metadata into custom packet headers. So here is a picture of our custom packet format. The netMC header is encapsulated as the layer for payload of the packet. The netMC header contains various metadata fields such as request type, packet ID, packet order, number of keys, index for keys targeting the same server, index indicating where to read from, a client flag, and the list of target server IDs. So these metadata fields are compact, typically around 20 bytes. So they introduce only a small overhead. Here's the architecture of netMC. The client puts extra metadata to the packet header to assist the switch. And it also performs reply aggregation. In the switch data plane, the system identifies the current key group, checks if there are more key groups to process, assigns the target storage server's IP for the current key group, and generates sub-requests. Here, a key group refers to a subset of keys belonging to the same target server. Next is the detailed process. We suppose that the client sends a Multiget request for keys A, B, C, and D. These keys are distributed across three storage servers using HASI partitioning. To make splitting easier, the client first sorts using a HASI function to identify the target server for each key. And then the client inserts metadata about Multiget request into the packet header. As a result, the keys are grouped together by server in the packet. In this example, we end up with 3 key groups. The first group is AD, the second group is B, and the third group is C. Now let's move on to request splitting inside the switch. When the switch receives the packet, it first checks whether it's already a sub request. In this case, it's not, because this is the first packet of the Multiget request. So the switch identifies the current key group, in this case AD, and updates the metadata fields such as key index and number of key like this. Next, the switch assigns the target server address for the current key group. It first reads the metadata in the packet header, and based on that, it looks up the server ID table. The table contains metrics rules that tell the switch which server its key group should go to. In this case, the rules indicate that the current key group should be sent to server 1. So by this information, the IP address of server is 1001.101. The switch then updates the destination IP metadata field with its destination address. Before forwarding the packet to server 1, the switch checks whether there are more key groups left to process. As shown in the picture, it checks the metadata field key index, but it is not 0. It means so there are more groups to process. So since the BC group is still remaining, the switch clones the packet. It then marks the cloned packet. It is cloned. And then the original packet, which enters the key group AD, is sent to server 1. Meanwhile, the cloned packet re-enters the ingress pipeline for further processing. It goes like this. And then after the cloned packet re-enters the ingress pipeline, the switch checks again if it's a sub request. So this time it is because the clone field is 1. So the switch updates the metadata to process the next key group BC. So this entire process repeats until all key groups have been scripted and dispatched. Let's move on to reply aggregation at the client. We suppose that the reply for keys BC has already arrived, like this. And now the client receives the reply for AD. The client appends all the key value pairs to its key array and value array. Then it checks whether this is the final sub-reply for the Multiget request by consulting the sub-request array. So it matches with the received packet number of key and inside the sub-request array. If so this becomes 0, and this means ID 1000 first Multiget request is done. So the client commits the 1000 first Multiget request. Now let's take a look at the evaluation. We implemented NetMC using an Intel Tofino switch and 8 commodity servers. The 2 nodes are acting as clients. Another node is for the coordinator node, and the remaining 5 nodes are storage servers. Our baselines are ClientMC, following a client-based architecture, and CoordMC, following coordinator-based architecture. For the workload, we use a 5% write ratio and a GPM distribution to simulate a skewed access pattern in real world. First, we compared throughput under different skewness levels using a key value store, TommyDS. In the graph, the gray bar represents ClientMC, the navy bar is CoordMC, and the hatched bar indicates NetMC. As the result shows, NetMC consistently outperforms most baseline methods, regardless of the workload. Under heavy skew, NetMC achieves 11% higher throughput than ClientMC, and nearly 2 times higher throughput than CoordMC. So NetMC is resilient to the skewness in key distributions. Next, we looked at the latency versus throughput results. In the graph, the gray line represents ClientMC, the black line is CoordMC, and the blue line is NetMC. As shown, NetMC achieves the lowest latency across almost all throughput levels. CoordMC has extremely high tail latency, so it doesn't even show up on the graph. At 256,000 requests per second, ClientMC shows about 66% higher latency than NetMC. We also evaluate the performance with Redis to demonstrate that NetMC can work with real-world applications. Redis is widely adopted in-memory key value stores for many production services. In these Redis experiments, NetMC again performs best across all distributions. NetMC outperforms ClientMC by an average of 15% and CoordMC by 67% in throughput. For scalability, we evaluated NetMC under both skewed and uniform workloads. In all cases, NetMC achieves the highest throughput. When using only 2 servers, NetMC outperforms ClientMC by 90%, and NetMC also outperforms CoordMC by 86% on average. We also evaluated performance with different Multiget sizes, that is, varying numbers of keys per request. In terms of throughput, NetMC is 70% faster than ClientMC and 5 times faster than CoordMC on average. Even in 32 keys per second per request, NetMC shows 55% lower latency than ClientMC. This result shows that NetMC is robust to workload dynamics, even as the number of keys per Multiget increases. And then we evaluate the impact of value size on the performance of NetMC. As shown in the graph, NetMC consistently delivers the best performance across all value sizes. In contrast, Both ClientMC and CoreDMC show a decline in throughput as the various size increases. This is because client-side coordination overhead is added when the various size increases. To summarize, we presented on NetMC, a network accelerated multi-get coordination architecture. NetMC can achieve high throughput, low latency, and scalability at the same time by splitting coordination networks, coordination tasks between switches and the clients. We believe this approach opens the door to further leveraging in network computing to improve coordination in distributed systems. Thank you.
Thank you so much.